Hello again, everyone. This is chapter 7.2, Spanning Trees. All right, we're continuing on with our spanning trees. Again, remember the first three properties. Go ahead and take a second to review them now. The first property being that there is only one path joining any two vertices. The second property being that every edge is a bridge. And the third property being that every tree has exactly one less edge than it does a vertex. Now here's property 4. The property 4 deals with redundancy. And if you think about redundancy, a redundancy has to do with anything extra. If you had a third arm, that third arm would be redundant because you can do everything with your two arms. So a redundancy is something that is extra in your graph. So if we look at a graph that has n vertices and m edges, remember n minus 1 is the number of edges that the graph should have, so that's this. And if you take the number of edges that the graph does have, that's m, and you subtract from it the number of edges that a graph or that the tree should have, then you should get the extra edges. So if I'm looking at an example, let's do a triangle. There are 1, 2, 3 edges, and there should only be 1, 2, 3 minus 1. So the redundancy is 1. Okay, if I did, let's do the other example I was working with here, the completed graph of 4. Actually, this is not a completed graph of 4, is it? This is the completed graph of 4. There are 1, 2, 3, 4, 5, 6 edges, and 4 vertices minus 1, so that's 3. There are 3. The redundancy is 3, which means that there are 3 extra edges that need to be removed. Now that just assumes that, well actually let's do a one that is a tree. Let's do this one. So that's 1, 2, 3 edges, and 1, 2, 3, 4 minus 1 should be 4 minus 1 edges, and that equals 0. So the redundancy is 0. If the redundancy is 0, then you know you have a tree. But these are positive numbers. Redundancy typically is listed as positive numbers, but imagine that graph right there. It's disconnected, but you could also compute the redundancy for this one. So if I have 0 edges, and I have 2 vertices, I should have 1 edge. So it is -1 is the redundancy. If your redundancy is negative, that tells how many edges you need to add. If your redundancy is positive, it tells how many edges that you need to remove. And of course, if it's 0, then you know you don't have to add or remove anything. It's a tree. So look at figure A here. You'll notice that immediately there is a circuit in there, and of course we want to remove, if we count them, it has 8 nodes and 8 edges. Now remember we have, or links, I should start saying links. Anyway, there are 8 edges and 8 nodes and 8 links, and we know we have 1 less link than we do nodes. So we know that our redundancy is 1. So we will have to remove 1 edge. But think about what that means. Somehow, for this particular graph, and again, we're only looking at figure A, we have to break the circuit. So we know we're removing 1 edge. There also happens to be 1 circuit in there. So if we remove BC, we now have a spanning tree. That's one possible spanning tree, but we could have also removed CG, which creates another spanning tree, or we could have removed BG, which would have removed, or which would have created yet a third spanning tree. Now, some things to note here. We had one circuit listed, and we knew that we had to remove one edge. The redundancy was 1. There are 3 edges, or 3 links to my circuit, so therefore there are 3 possible spanning trees. That's a theme that's going to kind of carry us forward as you're looking at these. You can deduce how many possible spanning trees there are based on how many edges that need to be removed. So this, and I think some of the following one is just reiterating what I said. If you go through and read these slides, you'll get an understanding. Maybe take notes from them. And this explains why there are 3 different spanning trees. Okay, so we're looking at this figure here. It's a fun little star-shaped object. Is it a tree? It's not a tree because we have a circuit. We have, if you count out the redundancy, it has 1, 2, 3, 4, 5, 6, 7, 8, 9 edges. 9 nodes. And 1, 2, 3, 4, 5, 6, 7, 8, 9 links. So 9 minus 1 is 8. So the redundancy is 1. Now we can remove the 1 here. We can remove the 1 here or here. Again, we have one circuit, and strangely enough, we have to remove 1 edge. In the circuit, there are 3 sides to the circuit, so we can deduce that there are 3 spanning trees. One tree looks like this. Now, let me make my writing bigger. One tree looks like this. One tree looks like this. And then the third tree looks like this. Those are the 3 spanning trees in that figure. How about this one? Again, figure out the redundancy. Let's see, that's 1, 2, 3, 4, 5 edges minus 1, 2, 3, 4, 5 minus 1 is how much we should have. So that's a redundancy of 1. And again, we have one circuit. We can remove this 1, this one, or this one, which means that we have 3 possible spanning trees. Now we're going to do this one in class, so pause the video and take a few minutes to try to work through this. We're working with a minimum spanning tree, so what you want to concentrate on removing first, if you have to, well, let's talk about the steps and then we'll solve it in class. When you're doing the minimum spanning tree, remember we are trying to figure out, first off, what's the redundancy, how many do I have to remove, and then we attempt to remove it to find out how many spanning trees that we can create. In this particular problem, notice that all of the links have values associated with them. So when you're breaking up these circuits, when you're bringing your redundancy down to 0, make sure that you choose the biggest link before the smallest. So take a few minutes to work through that, and I will see you tomorrow.